Structure, Introduction to Algorithm Complexity and Searching, Sorting Elements of Arrays, String and String Operations, Introduction to Recursion. In Unit 2, we have stacks and queues, Introduction to data structures like stacks and queues, operations of linked lists, representation of linked list, operations of linked lists such as transversing, insertion and deletion, searching, applications of linked lists, concepts of circular linked list and doubly linked list and their application. Stacks and queues using linked lists. Basic terminology. Binary trees and their representation. Binary search trees. Various operations on binary search trees like traversing, searching, insertion and deletion. Applications of binary search trees. Complete binary trees, extended binary trees, general trees, AVL trees, threaded binary tree, B tree. Searching and sorting, linear search, binary search, interpolation search, insertion sort, quick sort, merge sort, heap sort, sorting on different keys, external sorting. Unit 4, graphs, terminology and representation, directed graphs, representation of graphs and their transversal, spanning trees, single source shortest paths, Dijkstra's algorithm, hashing, introduction, hash functions, collision resolution techniques. Crash course already. Introduction to data structure and algorithm. Introduction, arrays and strings. Introduction to data structures and modified efficiently. Need to use more memory, more space. Conversely, if you want to save memory, your program might take longer to run. Abstract data type, ADT, a blueprint for a data structure that defines what operations can be performed on the data but not how they are implemented. For example, a list is an ADT. An array is a concrete implementation of it. Arrays. An array is a collection of items stored at contiguous neighboring memory location, one-dimensional. A simple line of elements, two-dimensional or multidimensional, a grid of matrix, rows and columns, basic operation, alright. Representation of array, this I know, print dot insert to comma. Oh, wait, we haven't done Python. What should I do? Does it mention which language we are going to use? Okay, we'll have to build these structures from scratch using pointers and structs. In 2D array, memory allocation. 1D array, elements are arranged in a single continuous block of memory. 2D array, stored in memory sequentially, typically row by row major order. Okay, this much I know. Unit 2, stacks, queues and linked lists. Simply linked lists. In C we use a struct to define node. It contains I got stuck here. Okay, I'm lost now. Binary tree node structure. Just like a linked list node has one pointer, a binary tree node has two pointers, left and right. Left and right. Okay, we just created two binary tree node on binary tree pointers. I don't understand the code though. Binary search, iterative implementation. I don't understand the code. Graphs and hashing. Graph representation. Adjacent C matrix. The easiest way to represent a graph in C is by using a 2D array. If node I is connected to node J, did I say it? Alright. Hashing, linear problem for collision. If a spot is an array is taken, look for the next available spot sequential. Most of the code. Okay, I know the theory. Stacks is last in first out. Alright, and queues is first in label maker. You type in the name. The label maker does a quick mathematical calculation and spits out number. You walk I do know the basics and most of the theory. Now this is what I don't know. Strict malloc and this sign. The dynamic memory blueprint, struct and malloc. Theory, you know, data and pointer to the next node, and so we build this custom container using a struct node. Array traversing pointer with the next pointer. Now let's create a simple 3-node list. This is how we use malloc and arrow query. To set this up inside the main. Think of a note as an envelope. In C, you write this. To create an envelope called note, inside the envelope there are two boxes. Data and there. Next. Here. Okay. Okay, this makes more sense. Moving your view current equals to currently looking at our address 1000, we execute this line function. This is a very common exam question. How do you add a new node to the front of a linked list? Inserting a node at the front. Imagine you already have a chain of envelopes. You want to introduce a brand new envelope and make it the new head, the very first item in line. To do this safely without dropping your existing chain, you need only 3 steps. Create the new envelope, struct node new node equals to struct node malloc size of struct node. New node data equals 5. Point the new envelope to the current first envelope. Head is holding the address of the current first item. Now that the new node is securely connected to the rest of the list, we can officially declare it as the new start of the list. Head equals new node. I got an idea, not very confident though. In theory, a stack is last in first out. Can easily build this using which it remains exactly the same as our linked list. Node in data, struct node next. Look and place it right at the front of the line. Step 3, pop. Remove from top. To pop, we look at the top envelope, copy its data so we can return it. Shift top to the next envelope in line and then safely destroy the old envelope using free. Alright, we can go with Q. Thank you. DQ. I got something. I got little stacks and queues. Unit 3. Trees. Binary search tree. Emailing this, an envelope has one address slot. Binary tree. Each envelope has two address slots, left and right. The tree node blueprint includes this. We use recursion here because the exact same rule applies to every single branch we have. Okay. pointer traversal, left root right. Because of the way BST is structured, if you transfers it in this exact order, it will naturally print your data in a perfectly sorted ascending order. Blurry, at least I'm getting a hang of it. So I'll just move forward. Arrays are laid out. These algorithms are all about how we manipulate array indices, high, low, high to organize or find data. First is searching algorithms. Your syllabus covers linear search and binary search. Linear search, the brute force way. You look at every single element from left to right until you find your target. It doesn't care if array is sorted or not. Time complexity, or in worst case, you look at all elements. Binary search, the divide and conquer way. Crucial rule, the array must be sorted first. Instead of searching one by one, you check the middle element. If your target is smaller, you throw away the entire right half. If it is bigger, you throw away the entire left half. Complexity O log n, extremely fast, cuts the problem in half in every step. Include 0 and high size -1. Okay, the code seems I'll not be able to write the code. Second would be sorting algorithms. Let's look at two major sorting styles from your syllabus: a simple one, insertion sort, and a highly efficient advanced one, merge sort. Insertion sort. Wait a second. First, I'll have a glass of water. Insertion sort, like sorting a hand of playing cards. You split the array into a sorted part, and an unsorted part. You pick an element from the unsorted part and slide it backwards into its correct position in the sorted part. Point insertion sort int r. Okay. Logic. I do not understand the logic quite well. I'll just go with the yes, even though I didn't understand it completely. Graphs and hashing. Graphs. A graph is like a social network or map of cities, and like a tree which has a strict parent-child hierarchy, a graph can have loops, cycles, and cross connections. Vertices, nodes, the objects. Example cities. Edges, the connection between them. Example roads. Graph representation. Since C doesn't have native dynamic list, the most common way to represent a graph in an exam is using an adjacency matrix, a 2D array. Hashing. Hashing is an incredibly clever trick used to store and find data instantly over time complexity. Imagine you are building a database of phone numbers. Instead of searching through a list line by line, you use a math formula called the hash function to tell you exactly which array index a number belongs to. Handling collision, linear probing. What happens if two different phone numbers happen to yield the exact same index when run through the math formula? That's called a collision. One way to fix this in C is linear probing. The slot is taken, simply walk down the array index by index until you find the very next empty slot. Since I am not very confident, I think I will ask for some short questions. No, okay, I knew this one. Why did I opt the header? It was last in, first in, first out. Last in, first out? How is that possible? I confuse stack with queue. When implementing a queue using a linked list. In the left subtree. Must be completely sorted. It was merge sort. Alright, I got 2 wrong. I'm still not confident. Just go with more questions. Harder. Okay, it is actually harder. It cannot be the D. It cannot be option D because we don't free the variable first. Temp next here equals to it cannot be B there. No, it has to be okay. Wait, what? Hit next, temp next. Oh, alright. When parsing and evaluating postfix we did not cover this one. I'm not very confident with postfix expression evaluation. I'm not confident with this. How do I even solve it? When implementing a circular queue inside a stack, I don't know this one. Perpetrating